Hello everyone, welcome. Thanks for coming to this last session on our first day of POPL'. Our first speaker will be Michael. This is a distinguished paper, and he will be telling us about how to attack the challenging problem of mixing multiple languages in the same program. Take it away.
Okay, can you hear me now? Great, thanks. Okay, let's go. Hi, I'm Michael, and I would like to tell you about DimSum, which is a new approach for reasoning about multi-language programs in a decentralized way. And I will explain what I mean with this in a moment. And this is joint work with lots of great people. As you may know, in the modern world, many programs are not written in a single programming language, but consist of components written in multiple different programming languages. And if we, as programming languages researchers, see such multi-language programs, the obvious question arises, how can we reason about these multi-language programs in some nice modular fashion? But this is not an easy task, and I want to explain why based on this small example. So here we have a small main function written in C. This main function has a local variable x, which is an array of size 3. And this main function first initializes this array, then it uses the move function to copy some data around in the array, and finally it prints the last two values in the array. So why is this an interesting multi-language program? Well, first consider the print function. As you may know, printing is usually performed as some operating system, a specific system call, but C itself is a platform-independent language, so it doesn't have a native way to perform system calls. Instead, this print function is implemented in assembly, where we can use this platform-specific syscall instruction to actually perform our print system call. So this is the first key aspect of this example, which is that we kind of extend, we use this assembly print library to extend the C code with the ability to perform system calls. Let's move on. Particularly, let's look at the move function here. This, as you may know, move behaves like memcopy, but it also works when the two pointers point to overlapping memory. The interesting detail of the implementation of move here is that it's implemented using this locale function, which is some form of address comparison between the two pointers. But if you're an expert in C, you may know that in C one usually has an abstract memory model, where pointers are, for example, modeled as pointers to abstract blocks of memory which don't have an order between them. So actually implementing this address comparison in C directly is quite challenging. So what we do instead is we use the fact that in assembly we have a concrete memory model where pointers are just raw integers and point to a flat array of bytes. So we can implement this locale function very easily in assembly by just comparing the two integer arguments. So, and this kind of shows the second key aspect of this example, that we can kind of use assembly's concrete memory model to extend C with the ability to provide address comparison, to do address comparison using this locale function. The third thing I want to highlight about this example is this memcopy function, which is kind of a pure C function which doesn't involve assembly. So when we reason about this memcopy function, we ideally want to do this proof purely at the C level without considering assembly at all. So these three aspects show why this is actually an interesting multi-language program. Let's see how we can reason about it. First, let's look at existing approaches in the literature, and there are quite a few approaches for reasoning about multi-language programs. I want to highlight three important ones. First, there's the line of work by Hur and al., which culminated in the work of Pilsner. The core idea of this line of work is that we require each target language, target level program, in our case assembly program, to be specified using some source level program, in our case C program. If you do this, you don't need to do cross-language linking because each target level code has a corresponding source level code. But the downside, if you fix the source language as the specification language like this, is that we cannot actually verify the example we've just seen because these print and locale function actually do not have a specification at the source language. Second, let's consider some approaches that were explored in the context of CompSert. particular here, one common idea is to introduce a common interaction protocol to link between many different languages, in particular the different intermediate representation of the ComCert compiler. And here this common interaction protocol kind of fixes the mode of interaction, like the function call, how function calls work, and the memory model used by the languages. And this works well in the context of ComCert because ComCert uses one unified memory model. But the downside when you fix such an abstract memory model means that you actually again cannot verify the example we've just seen because it relies on the fact that assembly has a different concrete memory model to extend the ability, to extend the C code. Third, let's consider the line of work by Ahmed and collaborators on syntactic multi-languages. The core idea of this line of work is to take all the languages one cares about and embed them all into one large syntactic multi-language. And this line of work has pioneered many of the ideas in the work of multi-language semantics, but kind of one downside if you create such large multi-language and thus kind of fix the set of languages you reason about, is that when you want to reason about like a pure C program, for example, like this memcopy function, you still have to consider context in the multi-language. In particular, you still have to reason about assembly context, even if you're just reasoning about a pure C program. So let me restate these points in a different way. In particular, I want to phrase them as kind of Desiderata. What do we want from a framework for reasoning about multi-language programs, such that it can verify the examples like the one we've seen before? First, we don't want to fix the source language as the specification language, but we want to be able to link with target level code that is not representable in the source. Second, we don't want to fix the memory model, but we want to support languages and interaction between languages with different memory models. Third, we don't want to fix the set of languages up front, but we kind of want to allow language local reasoning in one language and then combine it with reasoning in other languages as necessary. In the paper, we also have a fourth point about not forcing a fixed notion of linking, but I sadly don't have time to discuss this in detail in this talk, and you can have a look at the paper for more details. But as you might guess from the slide, these Desiderata is exactly where DimSum comes in. So DimSum is now a framework for reasoning about multi-language programs, which is what we call decentralized. And with decentralized, we just mean that it fulfills these four Desiderata we've just seen. We call this decentralized because all these Desiderata are about not fixing something up front, but instead one should be able to kind of pick in some decentralized, flexible fashion, like which memory model, with specification languages, with which set of languages one cares about. DimSum achieves this by combining ideas from lots of existing fields, including process algebra, cryptic relations, and some work on angelic non-determinism. We've instantiated DimSum with three languages. First, Rec, a C-like language, ASM, an assembly language, and a mathematical specification language, Spec. We've evaluated DimSum by implementing and verifying a compiler from Rec to ASM, and by verifying two interesting case studies. One is the locally pointer comparison case study we've already seen. Another case study is an assembly coroutine library, which provides a new interesting coroutine abstraction to the Rec code. And all of DimSum is implemented and verified in the Cog Proof Assistant. In the rest of this talk, we're going to focus again on this local E example we've just seen, and we will see how we can reason about it in DimSum. So recall, here we have our example again with the main function, which uses memMove and then kind of prints the last two values, which means it kind of prints 1 and then it prints 2. So before we can start reasoning about this example, we first need to figure out what's actually the thing we want to prove. Well, first we can start by creating this onetwo program, which is just kind of the complete assembly program corresponding to this example. So in particular, we take the main and the memMove function and compile it, use our Rec to ASM compiler to compile it to the assembly level. Now that we're at the assembly level, we can just syntactically link it with these other assembly libraries. So I mean can just build one large assembly program which just combines all the instructions of all these libraries. For the specification, we will just use a very simple specification which just says, okay, the program prints 1 and then it prints 2. But there is still an important question, and which is how can we actually define this notion of refinement formally? And ideally, we want to do this in some decentralized fashion, where we don't fix any of the languages up front. Here is where one of the key ideas of DimSum comes in, and we take inspiration from process algebra and use labeled transition systems as a common semantic domain for expressing and comparing different languages. And we use the labels of these transition systems, or the events of them, to express the interaction between the programs and its environment. In particular, for each programming language, like here our assembly language, we have these semantic brackets which kind of turn the syntactic assembly program into a semantic transition system, which we also call module. For the specification, we can just directly write down the transition system. Once we're at this level of transition system, it's actually quite easy to compare these two programs by just defining refinement as simulation between the transition systems. And we can do this independently of the notion of labels used by these transition systems. Okay, great. Now we know what we want to prove. We want to prove that this kind of complete 1-2 assembly program refines the 1-2 specification. And the next question is, how are we going to prove this? Well, as you can maybe see a bit here, this will take a few steps. At the high level, there are kind of three main conceptual steps. First, we're going to modularize our proof by introducing a notion of semantic linking. Second, we're going to see how DimSum handles translation between different languages by introducing a notion of semantic wrapping. And third, we're going to perform the bulk of the verification at the rec level by using a language local verification in rec. Let's start with this first point. As you recall, our 1-2 program is just kind of this one big assembly program which just builds the union of all the instructions of all our libraries. In the first step, we replace this syntactic linking with a form of semantic linking, which you can think of as a form of parallel composition from process algebra. In particular, the events for assembly contain both outgoing jump events with a bang and incoming jump events with a question mark. And all this semantic linking is doing is synchronizing or matching an outgoing jump event of one of the modules with an incoming jump event in the corresponding other module that is being jumped to. So it kind of takes two assembly modules or two assembly transition systems and combines them into one larger transition system. Semantic linking has one key property, which is horizontal compositionality. Horizontal compositionality says that if we have M1 linked with M2, we can verify M1 and M2 separately, and then continue our proof by reasoning about the specification of M1 linked with the specification of M2. And this way, kind of the semantic linking enables modular reasoning because we can apply the refinements underneath the semantic linking operator. And we will use this a lot implicitly in the rest of this proof. Great. Now that we've seen how we can kind of handle the linking between programs in a single language, how can we actually handle in DimSum, handle the interaction between programs in multiple different languages? For this, consider the interaction between the memmove function and the locale function. So recall memmove calls locale, but memmove is written in rec, so we have again these semantic brackets to turn the syntactic memmove program into a semantic memmove rec level transition system, and you can see on the left, so this memmove transition system uses rec level events, so like calls and returns. But now for the locale program, it's an assembly program, so its transition system uses jump events. So how can we now link this rec level program with the assembly locale program? The way we do this in DimSum is that we introduce a notion of wrapper. And all this the wrapper is doing, it takes an rec level transition system as an argument and turns it into an assembly level transition system, which we can then link using our normal semantic linking operator to the locale program. And it does this by kind of applying the calling convention of rec to the to the rec events emitted by the original memmove program. And this shows kind of how DimSum achieves the second desideratum from before. Particularly, this wrapper kind of enables the interoperation between different languages, and it also can do the translation between different memory models, as we can see here. And the key technical idea which makes this wrapper possible is that this wrapper kind of encodes a form of relay guarantee protocol between the inner program and its environment, and we encode this operationally using both demonic and angelic non-determinism. And this is inspired by the work on conditional contextual refinement, which was presented earlier today at POPL. And if you haven't seen the talk, I encourage you to look at the recording. So now that we've seen this wrapper, where can we actually use it on our proof? Well, first we use it when reasoning about our compiled programs. So we have the compiled main and memmove programs, and we reason about them by applying DimSum's compiler correctness statement. This compiler correctness statement just says that if we take a syntactically translated program, so like a program generated by this syntactic compiler, this program refines the semantically translated original program, so like the program translated by applying the rec to asm wrapper to the original module. And this makes the reasoning a lot easier because instead of reasoning about the complex syntactic transformation of the compiler, we just need to reason about this wrapper which just kind of manipulates the events of the original program at the boundary. But we can also use this rec to asm wrapper in a setting when reasoning about loc.le. So recall we couldn't specify loc.le directly using a rec level program because rec does not support any form of address comparison. But what we can instead do is we can write down a semantic transition system at the rec level to give a specification for loc.le. And we can do this because in this semantic transition system, we can, for example, look directly at the block IDs of the location, something which you couldn't do in a syntactic rec program. And this way, we can now take the semantic transition system at the rec level and translate it to assembly using the wrapper and then kind of compare it against the original loc.le program. This shows that DimSum achieves the first desideratum because we don't actually need a syntactic rec program to specify this loc.le function, but we can instead specify it using the semantic transition system. Now that we've seen how we can kind of go from assembly to the rec level by introducing this wrapper, let us reap the benefits of this and see how we can perform the bulk of the verification as a language local verification at the rec level. Before we can do this, we need to do one small bookkeeping step where we kind of apply one lemma about commuting of semantic linking with the wrapper to combine all our rec aspects of this program to one large piece. Once we've done this, we now kind of have this large rec level program which contains like the original main and memmove code linked together with the specification, rec level specification for loc.le that we've just seen. And we can prove that this, or we can now handwrite a specification for this program which just says, okay, it calls the print function with 1 and then it calls it with 2. And finally, what we can do now is we can prove a pure language local refinement at the rec level to kind of perform, this is now kind of the bulk of the verification of this program, but this is kind of language local purely at the level of rec without involving any assembly. And this is a bit surprising that this works because, okay, on the one hand, loc.le was originally an assembly program, and on the other hand, all of this verification is kind of happening inside an assembly context, so there's still print around. But we can actually do this in DimSum because all our combinators, including the wrapper, are compatible with refinement. So we can actually apply this rec level refinement inside an assembly level, even inside an assembly level context. Once we've lifted, now performed this verification and lifted our specification to this high-level main spec, we just need to do one small proof at the end to join the main spec with the print spec. With this, kind of, we complete our verification of this example. So let me just briefly recap and see how DimSum achieves our Desiderata for multi-language reasoning. First, in DimSum, we don't need to fix the source language as the specification language because we kind of use this label transition system as the common semantic domain to express all our languages. Second, in DimSum, we don't need to fix the memory model, but we can use wrappers like this rect to asm wrapper to translate between different memory models. And third, we've also seen that in DimSum, we don't need to fix the set of languages up front, but we can perform language local reasoning, like this rect level reasoning, and then use compatibility of our combinators with refinement to use it in larger contexts. And finally, I haven't talked much about this fixed notion of linking, but briefly, DimSum kind of allows defining custom linking operators, so we don't need to fix the notion of linking. With that, I'm at the end of my talk. I would like to thank you for your attention, and I'm looking forward to your questions.
Yes, thank you very much, Michael. Do we have? Yes, we have plenty of questions.
This is Adam Chapala from MIT. The example that you highlighted didn't involve data abstraction, and I'm wondering what are the ergonomics of using data abstraction to allow a library in one language to depend on a library in another, say for some data structure?
Yeah, that's a good question. So in DimSum, kind of our specifications are just, expressed as transition system, so technically, this was for this talk. In this paper, we have this mathematical specification language spec, which, you can see as some form of I-trees for specifying the behavior of a program. And so you can use this specification language to kind of express the behaviors of maybe low-level data types in some mathematical way. So it's shallowly embedded in Coq, and then you can express your specification using that.
I-trees doesn't sound non-deterministic enough for classic abstract data types, but I imagine...
so you can do, a test event for doing full, both angelic and demonic non-determinism.
I see, okay.
And state, it has built in, yeah.
Thank you.
Hi, thanks for your talk. So I have a question about what sort of events can happen. Is that something that's fixed, or is that something you can extend? And also whether events are have to be equal at the borders, syntactically equal, or if that notion of equality could be weakened.
Yes. This is indeed a very, very good question. So in DimSum, the core framework of DimSum is generic over the notion of events. So the notion of module and the notion of refinement is generic over the notion of events. And what you then do is when you have a certain language like assembly, you pick a notion of events which kind of corresponds to that language. So we've seen the assembly events. If you define rec, we also pick a notion of rec events. And then you can define another language and pick your own notion of language. And then you can kind of use the wrappers to translate between these different events. And so for your second question, indeed, the notion of refinement we have fixes, uses syntactic equality between events. But this is not as restrictive as it might sound, because we can actually use wrappers to kind of encode more specific relay guarantee protocols, so more interesting refinements. And we have a discussion of, and we can even use wrappers, define wrappers language. So in the paper, we have the example of a rec-to-rec wrapper, which kind of allows us to do optimizations on memory. And there's some more discussion on this in the paper.
So I'm Alan Jeffrey from Roblox. So one of the things which, at least in the examples that you gave, seems to be fixed between the two languages is that there's a common notion of sequential computation between the two. So I'm thinking of examples like async await in some high-level language linked up against C. That doesn't seem to immediately fit into this framework. I was wondering if this is something you'd thought about and have an approach for?
This again is a good question. So there are two answers. So first, the answer is in the other example, which I haven't shown in the paper, is kind of a coroutine example where you then kind of use an assembly library to provide a new form of linking to rec, which is kind of a bit different than the usual linking because you're doing like coroutines, so like some calls become returns and so on. So we've explored this a bit, but in general, like concurrency or more complex examples like syncf8 would be very interesting case studies or challenges to explore for future work in this area and to see whether DimSum can also scale to such examples.
Cool, thanks.
Thanks for the question and thanks for